All right, welcome. So we've kind of gone through a high-level view of microcontrollers. We kind of peeled off the lid in a few videos to kind of see what's inside. We talked a little bit about design tool concepts, about how do you get your code into the microcontroller, kind of a very high-level view. So kind of last is our getting started guide, where we're going to look at high-level concepts. We're going to take a look at some of the nitty-gritty about hardware interfacing with a microcontroller. And I tell my students that if you could understand this, there's nothing you can't program, because there's nothing else. It's the concepts I'm going to show here. They're it from interfacing the hardware. It's all it's all window dressing after that, of making it fancier and making it more complex. But the fundamentals are in these slides. So to kind of have fun with this, we're going to look at the ACME Mark IV Warp Drive controller IC. So the Warp Drive controller IC is what's used in a Starship, to get to warp. So, this particular controller, 8-bit operation, good old 8-bit technology, kind of implements nice warp speed control, does dilithium power sequencing, systems monitoring. So we're going to look at, if we had this chip and we had to program it, what the typical flow is on a microcontroller, of how you make hardware work. So we're going to have fun, and see how this hardware gets programmed. So what I'm going to show you now is what you'll typically see in a reference manual. You're going to look up a particular peripheral, and it's going to have some name. So, for example, this is called the Warp Drive Unit, WDU for short, and it's going to tell you that it's going to have a certain amount of registers. Now, the first thing I want you to take a look at is it's going to specify the base address of the registers, and we're going to put it at 100 hex. And this is very common, where we don't necessarily specify the address of each register. We're going to specify them as a base address plus an offset. And the reason we do this, in some cases, some peripherals, there may be more than one. So we just document the offsets, and then the system engineers who made the chip might put more than one copy of the same logic. So this is very common to see this base and then offset notation. And in a future video, when we talk about C data structures, it actually makes perfect sense why they do this, because there's some really cool ways you can use to program it. You may see something like this, like some name for the register, warp control, and it might be documented with some sort of mnemonic, where the unit name underscore there's some other mnemonic for warp control. For example, we're going to have a Setpoint register right here. So this is called WDU set, and we're going to have a status register called WDU stat. And in each one of these cases, it's a base address from an offset. So, for example, the WDU stat is going to be at 0x0102. All right, and that's the physical address. Now, we're going to look at in a future slide of how we talk to, future video of how we talk to absolute memory locations in C. But for now, when I show these registers, just keep in mind that I'm just going to refer to them by this mnemonic. But we're actually talking to a memory address, a memory mapped peripheral. Because as I said before, everything in a microcontroller, all the hardware, is just a simply memory mapped peripheral. Now, in a data sheet or a reference manual, it's very common to see each register. They'll kind of lay it out graphically, like so. They'll mention its address. And here's some features you'll generally see. What they'll tell you is, the question is, what's the reset value, of this register, after a power on reset, or something like a watchdog reset, or any other reset source. And usually they'll show you, a bit like this bit, enabled dilithium reactor bit, starts at a 0, but the warp disables at 1. So what's its state after reset, because that's important to know. It'll kind of give a description or maybe another mnemonic of each of the functions. It may have some not used bits, or it may have bits that span or fields that span multiple bits. The other thing it might tell you is what you can do with that bit. Even though it's memory mapped, this peripheral's memory mapped, it's not like memory. It's not like you read and write for it necessarily. Some bits are. For example, warp engage is read or write. So if you write the bit, you can always read its state. For example, not used bits, write may no effect. It might always read as 0. It might tell you how it reads. It might read as undefined. It might not want you to read it. There might be some sort of undetermined behavior. And so you just look through these registers and you can kind of get a good idea of what it does. So what I like to do on any new peripheral is just look at the register set and how it's documented. You can get a good idea of how it works, just by looking at the registers. Now, there's not really any state information of how things are sequenced, but you can get a good idea of what's going to go on. So in our warp drive unit, in our warp drive controller, we have a warp set point, and here's an example of a field that spans multiple bits. So the warp factor is specified in a high dot low notation. So for example, like 8.2. So 4 bits for the high digit, 4 bits for the low digit, where you kind of have an imaginary decimal point. And then warp 8.2, you could specify as hex 82 or binary. And here's a good example of there may be invalid values. For example, if we programmed anything through A through F, which is 10 through 15, the hardware will just round it down to 9. So we cannot hit anything more than warp 9.9. So you'll often see this in a register set. Next is we might have a status register. And the whole idea of a status register is not to write anything. It doesn't control anything. It's to read the state. So we can look to see if the dilithium reaction started, if our plasma relay is ready. There might be, example, a condition code. In this case, we have a warp condition code. It may have, the warp drive is not ready. Maybe there's a coolant leak that you want to report with this code. And in all these cases, you notice they're read-only. Writing has no effect. So there we go. So let's look at how we'd actually program this particular. You may find this in a datasheet. How do you actually start the warp drive? So for example, it's going to tell you first, we have to set, the warp disable bit in the WDU WC register. Then we set the warp speed. Then the next one, it's going to tell you when you have to set a bit in to enable the dilithium reactor in the WC register. Next, maybe we have to wait for a bit to go high in the WStat register. Then we have to set a bit, start plasma precharge. Then we have to wait for a bit in the status register called the plasma precharge complete. And so you can kind of read through the state diagram here, or the sequence of what you have to do to make this hardware work. Nothing's rocket science, no pun intended. But this is how hardware works. There's registers, there's bits. You either have to test bits or set them. So by the time we get through setting all these relays and precharge units, finally, we can set a bit for warp engage, and then we can check to see if there's no errors. In this case, warp disable will automatically clear, so we can check that bit, if there's no errors. And then we can look at the condition code register, to see what's going on in the, the condition code field in the WDU stat. and then we can look at the set register for actual speed. So this is a very common, that, you know, while we're not programming warp drive every day of our life, this is not uncommon in the world to see, in the microcontroller world, to see some sort of sequence diagram where you have to read a certain set of bits, set bits, clear bits, toggle bits. So what I want you to take away from what we've just looked at here is that controlling all hardware and peripherals, controlling it simply relies on your ability to read, write the bits in registers or these memory locations. So the question is, how in the world do we manipulate individual bits in registers? Now, you may already know how. It's certainly easy to think about how do you just write a value or add a value, but let's say you just want to go to bit 5. Well, that's a pretty rudimentary thing in a microcontroller program to know how to do. And once you know how to do it, you can write your own hardware drivers. So that concludes our first introduction to these hardware interfacing concepts, part 1. In part 2, we're going to dive in and really look at how in the warp drive controller we set and clear these bits. And I'm going to promise you, if you can understand this next concept, there isn't any hardware you can't program. So why don't you come on back and we'll take a look at part 2.